Hello, you're welcome back. All right, so we're going to continue from where we stop. And previously, we actually looked at the Chattelier's principle, all right, on a chemical equilibrium. All right, so now, uh, Chattelier's principles actually state that um, anytime a system that is at dynamic equilibrium is actually being disrupted by the introduction of external constraint. Okay, now the external constraint actually include the change in temperature, change in pressure, or even change in concentration. Okay, so once you have that the state of equilibrium being disrupted by external constraint, the equilibrium constant will actually shift in a direction to neutralize the effect of the external constraint. Okay, so now we're going to be looking at this external constraint, all right, their effect, and of course how um, equilibrium constant actually adjusts in order to neutralize the effect of this external constraint. So we are going to start with the effect of change in temperature on a system in equilibrium. All right. So for us to understand the effect of temperature on a system in equilibrium, we should actually take note of these two type of reaction, the exothermic reaction and of course the endothermic reaction. Okay, so here I have an equation of course, this is just an example of an a system in equilibrium. All right, of course you can see forward and backward arrow. Okay, so I have the reactant and I have the product. So this is an exothermic. If this is an exothermic reaction, you know very well that the delta H of that reaction is always negative. Delta H of every exothermic reaction is negative. Okay, so what does it mean? What is the implication of exothermic reaction? All right, now exothermic reaction actually tells us that the forward reaction, right? If the reaction is exothermic, it tells us that the forward reaction actually leads to increase in temperature. Okay, the forward reaction actually leads to the increase in temperature because it is an exothermic reaction, while the backward reaction, okay, actually leads to reduction in a decrease in temperature. So backward reaction, okay, is actually a decrease. Okay, so now that is the very first step. So for an exothermic reaction, you know very well that forward is leads to an increase in temperature and backward leads to a decrease in temperature. All right, so now what happens when there's an increase, when the system in equilibrium actually experiences an increase in temperature? Okay, so when the temperature of an exothermic reaction in equilibrium actually increases, all right, when the temperature change the temperature, okay, increases, then you know very well that the equilibrium constant is going to shift in the direction that leads to the decrease, because equilibrium constant will always shift in opposite direction to the effect of the external constraint. So So if I have an increase in temperature that is okay imposed on this system, then definitely the equilibrium constant will shift in the direction that leads to a decrease in temperature. Okay, so that simply means that the equilibrium constant K, all right, we actually shift. We shift to the left. All right, we shift to the left because the backward reaction, okay, actually leads to a decrease in temperature. So that means equilibrium constant will shift to the left, that will actually lead to more production of the reactant. Okay, so equilibrium constant is going to shift in the direction of the reactant. So it will favor the backward reaction. It's either you say that equilibrium constant shift to the left, or equilibrium constant will shift in the direction that actually favors. All right. So the shifting of the equilibrium constant actually favors the backward, the backward reaction. So that is more production of the reactant. But on the other way around, if all right, the the change in temperature, okay, is such that that's it actually decreases. All right, if the temperature decreases, temperature of the system decreases, then equilibrium constant, of course, we shift this time around to the right because if you decrease the temperature, the equilibrium constant will shift to the direction of increase, and the direction of the increase is actually is in the direction of the forward, all right, forward reaction. Okay, so the equilibrium constant will shift in the direction that will actually favor the forward reaction, that is C plus D. Okay, the product will be favored. Okay, so favors the forward reaction. All right, so I hope that is well understood. Okay, but if what we are looking at is a reaction, okay, that is endothermic. So if the delta H of the reaction is actually positive, so we know that such reaction is endothermic. Okay, now the implication of endothermic reaction. Okay, so the implication is that the forward reaction, all right, for an endothermic reaction, leads to decrease. Every endothermic reaction, that the forward reaction always lead to decrease in temperature, while the backward reaction, okay, actually leads to the increase in temperature. All right. So now in that case, for an exothermic reaction, okay, anytime you have the temperature, anytime you have the temperature decrease, the temperature of the system decrease, okay, then you know very well that the equilibrium constant K will actually shift in the direction of increase. So that simply means that the equilibrium constant will actually shift to the left. It will always shift to the opposite, okay? So which eventually favors the backward reaction, which favors the backward reaction. So, of course, understanding how this works, we can be able to explain exactly what happens if the system actually experiences an increase in temperature. Okay. All right. So that is if for the effect of temperature. Now let's look at the effects of pressure. Now, the effect of pressure, all right, the effect of change in pressure. The effect of change in pressure is only noticeable in reaction that involve gases. All right. So we'll talk about pressure when the reaction actually involve gases. So now from the equation of reaction, how do we know the direction of the reaction that leads to the increase in pressure and the direction of the reaction that actually leads to the decrease in pressure? Okay, so of course, for me to actually illustrate that, I'm going to use a typical example. Okay, Let's look at a typical example of a reaction between nitrogen gas, okay, plus hydrogen gas to form ammonia. All right, so for us to know the direction, of course, this is a forward and it's a reversible reaction, okay? So the arrow will be forward and backward, okay? Now, for us to be able to know the direction that actually leads to increase in pressure just from the equation, because you get to know that from the equation, we have to balance the equations so that we know the side that have a greater number of moles. Remember, the more moles of gas molecule that you have in a container, the more pressure there is that, okay? So let's balance that. I have two atoms of nitrogen and of course two atoms of hydrogen, but here I'm having three atoms of hydrogen. Okay, so for me to actually balance hydrogen, I will put three here to have six. By putting three at the back of hydrogen, all right, having it will now, okay, it will give a total of six atoms of hydrogen at the reactant side. Okay, so and of course at this side I'm having three atoms of hydrogen. So for me to balance that, I have to put two here. So that's going to be six atoms of hydrogen. Six atoms of hydrogen at both sides of the equation is balanced. All right. Then I'm having two atoms of nitrogen and of course two atoms of nitrogen. So it is actually balanced. So let's look at the total number of mole. Right. Nitrogen here is 1 mole. Hydrogen is 3 mole. Okay. So for the reactant side, the total number of mole is 4 mole. All right, so here I'm having 2 mole. Okay, for the product, the total number of mole is 2 mole. So as you can see, the forward reaction, okay, leads to increase in pressure. All right, increase in pressure. While the backward reaction, oh, please pardon me, the forward reaction, I have a lesser number of mole. Please pardon me. All right, the forward reaction, I have 2 moles, and the backward reaction, I have 4 moles. So forward reaction actually leads to decrease in pressure. Backward reaction, of course, leads to increase in pressure. So having understood this now, it is very easy to know exactly how the equilibrium constant will react anytime there's an increase in pressure or decrease in pressure. Okay, let's say there's an increase. Okay, so let's look at a situation where there's increase in pressure. So if there's an increase in pressure, okay, then you know exactly where the equilibrium constant will shift. The equilibrium constant will definitely shift in the direction that leads to a decrease in pressure. So if there's an increase in pressure, so the equilibrium constant will actually shift to the right. So which actually will lead to the more production of ammonia. All right. So more production of ammonia will be favored. So I invariably can actually conclude that such will favor, okay, the forward reaction. So forward reaction is favored, okay. So the forward reaction of the system is favored. I hope that is well understood. Okay, so as simple as that. So vice versa. So if there's a decrease in pressure, the equilibrium constant will actually shift to the direction of the increase in pressure. So the equilibrium constant will shift to the left, which actually leads to the yield of gonna lead to the yield of more nitrogen and of course hydrogen gas. So this is really very important because in exams, okay, you'll be asked, and for you to be able to answer, you have to make sure that you balance the equation of reaction. Of course, if the equation is balanced, okay, you have to inspect the direction of the reaction that leads to the increase in the pressure and the direction that actually leads to decrease in pressure before you can answer the question. All right. So now um, the same principle holds for change in concentration. Of course, concentration is basically significant when the reaction is in an aqueous medium. All right. So let's say you have A plus B. All right, reacting to have C plus D. So okay, now in this case now, I don't need to actually get to of I don't need to know. Okay, I don't need to investigate which part of the reaction leads to an increase in concentration since everything is in one solution. Okay, of course everything is in a solution. All I just need to know exactly what happens when more reactants are being added. So when you increase the concentration, when you increase the reactant, all right. So when you increase the reactant, then the equilibrium constant, in order to neutralize the amount of reactant that is actually being increased, the equilibrium constant will actually shift to the right, okay, to form more products. So if you add more reactant, if you increase the concentration of the reactant, more product will be formed. All right. Okay. And of course, if you happen to decrease the concentration of the product, let's say the product now, you keep on as you remove the product to decrease the concentration. Okay. So once the concentration of the product is being decreased, the equilibrium constant will go to the side of increase, then the equilibrium constant will shift to the left, all right, so that more reactant will actually, all right, more reactant will react to give more product. Okay, so that is just the principle and of course the logic behind Le Chatelier's principle. So if you understand the principle and the logic, you'll be able to answer any question. Okay, so now let's see the industrial application of Le Chatelier's principle application. All right, so there are two application, all right, two industrial process that actually apply Le Chatelier's principle. One is Heber process. Okay, Heber process is an industrial process that is used in the manufacture of ammonia. All right, in the manufacture of ammonia. Okay, which you have hydrogen molecule reacting with nitrogen. All right, then of course that actually yields um, ammonia. Okay, so we've actually written this equation and we balanced it. Okay, we balanced this equation, so I don't need to balance it. All right. So you know very well that first of all, uh, this industrial process, okay, actually the forward reaction, all right, the forward reaction actually um, leads to a decrease in pressure, but that is not exactly what is actually employed in this process. Okay, what is employed is based on the nature, all right, on the enthalpy of the reaction. So the enthalpy of this reaction is exothermic, all right. Of course, it's negative, so it's an exothermic reaction. You know very well that for an exothermic reaction, okay, forward actually leads to a decrease. Okay, forward, please pardon me. Forward reaction leads to an increase in temperature. Okay, forward reaction leads to an increase in temperature, while backward reaction leads to a decrease in temperature. Okay, so now want to actually ap- apply an external constraint, all right, so that we'll have more ammonia being produced in this industrial process. We want to get more ammonia, more production of ammonia. All right. So, what do you think is going to happen to this system? What should we do to this system so that the equilibrium constant, okay, so that the equilibrium constant will actually shift to the right. Okay. So now you know very well that if we actually lower the temperature, if we decrease the temperature of the system, then it will cause the equilibrium constant to actually shift to the right. Okay, so uh, the equilibrium constant will shift to the right. And that shifting to the right will actually lead to the production of more ammonia, all right? So that means in this industrial process of producing ammonia, all right, okay, so for you to have more yield of ammonia, all you just need to do is to try as much as possible to decrease the temperature of the reacting system so that the equilibrium constant will shift to the right to actually yield more production of ammonia. All right. Okay, so this one is the Haber process. Then we'll now have another process known as the contact process. All right. So the contact process also uh, operate with this using the same principle of Haber process. Contact process is a process in which sulfur 6 oxide is actually being produced using sulfur 4 oxide. All right, plus oxygen. So it's actually a reversible reaction. So this actually yields sulfur 6 oxide. And you can also balance this. If you balance this, you're going to have 2 here. And of course, there's going to be 2 here. Okay, so the enthalpy also is negative. Okay, so because the enthalpy is negative, you know very well that for us to yield more sulfur 6 oxide, okay, we'll have to decrease the temperature of the system so that the equilibrium constant will shift to the right. All right, so I hope you understand the principle behind this. Okay, now we're going to look at another part where you have this equilibrium, all right, and of course, uh, Le Chatelier's principle in action. Okay, so we are going to be looking at acid base equilibrium. Okay, now for us to actually understand that, let's start with the equilibrium of the acid. You know very well that an acid basically is okay, and it's an aqueous, right? In most cases, solution. Okay, we know that an acid is actually a substance that produces hydrogen ion as the only positive ion when actually dissolved in water. Okay, so when we treated acid, we look at an acid as let's say HCl, okay, as a substance that actually produces H plus Cl minus. But in actual sense of it, this is not all right. How we are, how to write the equation, all right. The actual sense of it, or the what actually happened when an acid dissolves in water, all right, is actually different from what we actually write here. This is just a simplified form of the equation. What actually happened is that this acid, when it dissolves in water, right, there's going to be a reversible reaction, okay, which might be in a state of equilibrium, and the positive ion is not actually hydrogen ion, but it is hydrozonium ion. Please take note. All right, hydrozonium ion. So what actually the positive ion of an acid, all right, is hydrozonium ion. So in case you are being asked in exam, okay, so hydrozonium ion, then of course this is the negative ion. So this system is actually in equilibrium. So that means the strength of the acid is actually dependent on the direction of the equilibrium, all right, that is actually favored. So when there is when the when the equilibrium constant actually favor the forward reaction, that leads to more production of this hydrogen ion, then you now have that okay, it will actually tell you that such acid is what a strong acid. Why? Because there's more production of hydrozonium ion. Okay, so hydrozonium ion is actually what is representing this hydrogen ion. So the more concentration of hydrozonium ion, the more strength, the more strength that acid will have. So I hope that is well understood. Okay, so I think this is basically what I need to actually explain, right? And I think also I can also write the equation of that of a weak acid. So you know how this is gonna be. This also is going to be a reversible reaction, okay, in which the negative ion is C H3COO minus, and of course plus. All right. So I hope that is well understood. So because of that, now we can actually use understanding how this work. We can actually use it to analyze the pH, okay, or we can actually use it to measure the pH of a salt, the pH of a salt solution. Okay, someone will ask a question: does a salt solution have a pH? Can uh, uh, normally, all right, a salt solution is supposed to uh, give a neutral, all right, a neutral solution, as in it's supposed to be neutral to pH. But the only salt solution that is neutral to pH, or what determines if a salt solution is neutral to pH, is dependent on the acid, all right, and the base that is actually used to form the that salt. Okay. Now, please take note of this. If you have a salt that is actually formed from strong acid plus weak base. So if you are being as such, what would you think would be the pH, all right, of such a salt solution? Of course, the pH of such salt solution will be acidic. So that means the pH will actually be less than 7. A pH less than 7 is acidic, right? Because this salt is actually formed from a strong acid and a weak base. So such salt will be acidic because there's more of the strength of the acid compared to that of the base. All right. Okay, but if what we have is a weak acid, then and then the base is actually strong base. Then you know exactly what is going to happen. Such solution will be alkaline, so definitely the pH will be greater than 7. Okay. All right, but if we have the two, if two of them are weak acid plus weak base, okay, so that means they are of equal strength, then definitely this is the point where you now have uh, a neutral solution. So the pH will be 7 approximately, and the same works with strong acid plus a strong base. Okay, then pH also, pH will be neutral, will be 7. And that is why sodium chloride, because all right, sodium chloride is actually neutral to pH, because chloride is actually formed from a strong base, which of course is sodium hydroxide, and of a strong acid, hydrogen hydrochloric acid. So those two are strong. So to end up giving you a neutral solution. All right. So I hope you understand this. So I'm just giving you the basic uh, important information that you are definitely going to counter in exams. Okay, so this logic are really very important for you to actually understand, because it will help you to answer most questions in examination. All right, so that is it for this video. We are going to look at more in the next video. Okay, so see you in the next video. Thank you very much.